Hello, this is a number theory video on Diophantine equations. One of the classic number theory topics, in the double meaning. It goes back to ancient times. Diophantus was a Greek mathematician in Alexandria, which is on the Mediterranean Sea in Egypt. And maybe we can discuss more about him on the discussion boards. The idea of a Diophantine equation is quite simple, accessible even to middle school students. So here are a couple of equations. 20x plus 35y equals 233. 20x plus 35y equals 235. And we want integer solutions. The idea of a Diophantine equation is we want integer solutions, and we're going to be doing linear ones in this video. We're going to have x to the first power and second and y to the first power. It could be that you would do quadratics, but these are going to be linear Diophantine equations. So I'd like to give you the idea of Diophantine equations because it's easy to grasp by using a graph and looking at it visually. Okay, this is GeoGebra, and I will put the link to this GeoGebra down in the description. The equation that we're trying to solve right now is 6x plus 8y equals 10, and you might think in your head what the solutions are. This is a equation. It's kind of in the old-fashioned standard form that we used in the other century. We don't use this form very much anymore, but we could solve it for y and have it y equals mx plus b. And what we're interested in as we move along our curve here is we'd like an ordered pair x, y that's going to be an integer pair. Like right here is 1. That was supposed to turn red. How come that didn't turn red? Huh? Okay, now it has turned red the way it's supposed to. I have the ordered pair negative 5, 5. Let's check it. Negative 5 times 6 is negative 30. Positive 5 times 8 is 40. Negative 30 plus 40 equals 10. So this has a solution. There are other solutions where the graph paper grid, this one at negative 1 comma 2 works. This one right down here, if I can get it to stay there, positive 3 comma negative 1. In this particular case, I do not get any solutions here in the first quadrant where x and y are both positive. In some applications, we would want x and y to be positive. Now let's change the 10. Let's make this 13. Now let's see if we can move our point and find a place where the graph paper crosses. And I can work and work and work and work, and never does this line go through the grid of the graph paper. This Diophantine equation does not have a solution. You might think about why this does not have a solution based on what we've already learned in our number theory class. As you can imagine, it comes down to the greatest common divisor of 6 and 8. The GCD of 6 and 8 is 2. So as long as this number over here is a multiple of 2, like 58, this is going to have solutions. However, if this number over here is not a multiple of the greatest common divisor, it is not going to have a solution. Let's prove this. Existence of solutions to a Diophantine equation. Of course, we have integers because this is number theory and we work with integers. D is the greatest common divisor of A and B. Furthermore, D divides C. My Diophantine equation, AX plus BY equals C, has a solution. This is a very straightforward proof from the number theory results that we already have in place. So we have the given information about the greatest common divisor, and we have the given information about D dividing C. Let's start with D divides C. This is a given piece of information. This implies, from our definition of divides, there exists K in the integers such that dk equals C. You might be able to anticipate the next step. I encourage you to pause the video and see if you can write the theorem yourself. The proof yourself, that is. D equals the greatest common divisor of A and C by Bezout's theorem says there exist two integers. Maybe I will use W and V in the integers such that a linear combination of A and C give D. AW plus, whoops, I have a mistake here. It's supposed to be A and B. Let me fix that. AW plus BV is equal to D. But I don't want a linear combination that just gets piddly old D. I want a linear combination that gets C. So, as usual, I'm going to combine our information. I'm going to multiply through by K. So we have AKW plus BKV equals K times D. But what's K times D? K times D is C. So we have AKW plus BKV equals C. Our solution here is going to be KW and KV. This is the end of our proof. We might just take a quick peek at our book here. AX plus BY equals C is our Diophantine equation. And here is our result that we are going to have integer solutions if and only if D divides C. In our proof, we just proved it one direction. But we can say more. If we have a particular solution, there are infinite many solutions. And here are the formulas for generating an infinite number of solutions. Let's prove this. So we have integers, and we have a particular solution to our equation, AX plus BY equals C. The particular solution is X naught and Y naught. Our conclusion is that there are infinitely many solutions, and the solutions are given by these expressions. Now, if we take a look at these expressions here, Notice that we're dividing by d. b is divisible by d, so this looks like a fraction, but it's actually going to be an integer because d is the greatest common divisor. D also divides a. The other thing you'll notice that here we have addition and here we have subtraction. This is not a typographical error. T is an arbitrary integer. If we plug in 0, we just get x naught and y naught. Plug in t equals 1, you get another solution. T equals 2, another solution. T could be negative. Any integer will give you another ordered pair. Okay, let's prove this. We're going to find this proof to be quite straightforward. We do have to pay attention to our notation. From our given, we know that ax naught plus b y naught equals c. X naught, y naught was a solution. Now we're going to substitute in these would-be solutions and see what happens. A times x naught plus b over d t plus b times y naught minus a over d t. Once again, you might pause the video and see if you can finish the proof. I'm going to do distributive property, so I'll have ax naught plus ab over dt plus by naught, looks like I ran out of room, minus ab over dt. That's nice. ab over dt minus ab over dt is 0, so I have ax naught plus by naught. This whole side comes down. And we know above that ax naught plus by naught was c, so I can make my conclusion a times x naught plus b over d t plus b times y naught minus a over d t equals c, and I have shown that this is a solution, and my proof is done. Now let's apply our theorem. Find all solutions, find all solutions or prove that there are no solutions. If there are solutions, list 3 specific ordered pair answers and give algebraic expressions for x and y. So in our first example, the GCD of 20 and 35 is 5. 5 does not divide 233. Therefore, no solutions. In our second example, we still have 20 and 35 having a GCD of 5. 5 does divide 235, so there are solutions. Now, how do we find them? Well, we use our linear combination, which we learned in previous weeks. And in some cases, you may need to use the Euclidean algorithm to get your linear combination. Now, we're not going to get the linear combination for 235. We're going to get the linear combination first just for 5. And let me see if I can do one here in my head. Okay, I can take 20 times 5, that'll give me 100, plus 35 times negative 3, which is, oops, I think I want to do it the other way around. Yeah, I want to do it the other way around. I want a negative 5 to get negative 100 and a positive 3 to give 105. And this gives me 5. We don't have a solution yet for the Diophantine equation. I need to multiply through by whatever it takes to get 235. So I'm going to take 235 divided by 5. So I'm going to need to multiply through by 47. And since I'm going to do this on both sides, I'm going to make that a different color. I'm going to multiply over here by 47, and I'm going to multiply over here by 47. So I get 235 on this side, and over here, negative 5 times 47. I think I can do the break apart strategy. 40 times 5 will be 205. Well, it's negative 235. That's coincidence unless I've made a mistake. And 40 times 3 is 120. 7 times 3 is 21. So I believe we have 120 plus 21 is 141. If it's on the calculator portion of the exam, it's a good idea to check that on a calculator. So my x naught is negative 235, and my y naught is 141. So now we're going to be writing our general my general solutions. And I don't want x naught on the left-hand side of the equation. I just want x. B over D. B is 35. D is 5t. I'm going to simplify that in just a minute. Y is y naught, which is 141, minus a over d. A is 20 over 5t. Now let's simplify this. X equals negative 235 plus 7t, and y equals 141 minus 4t. And so we were asked to give 3 ordered pairs here. We have negative 235 and 141. And now let's maybe just use t equals 1. If we use t equals 1, this is going to be negative 228, I believe, and 141 minus 4 is 137. Lots of good mental math here. Let's use maybe t equals negative 1. T equals negative 1. I get negative 235 minus 7, which is negative 242. And 141 plus 4 is 145. Now, this would answer our question. Let's see what our question was. Our question was to list 3 specific ordered pairs and algebraic expressions. Here are the algebraic expressions, and here are the specific ordered pairs. Now, let's say that we wanted positive answers for both of them. Let's see if we can get positive answers for both. So this will be an extension. we're trying to get positive solutions. And once again, this works out very nicely. Very nice algebra. Negative 235 plus 7t needs to be greater than 0. I'm working with inequalities. And I want 141 minus 4t to also be greater than 0. In my first inequality, if I add 235 to both sides, I get 7t is greater than positive 235. And I divide both sides by 7, and I get t is greater than 33.57 blah, blah, blah. On the other hand, negative 4t is greater than negative 141. And I'm going to divide both sides by negative 4. As you may remember from a previous algebra course, if you divide an inequality by a negative number, you must change the direction of the arrow. So I'm going to divide the left-hand side by negative 4 and get t. The greater than sign becomes less than negative 144. I'm sorry, negative 141 divided by negative 4 is 35.25. So interestingly enough, I need to have a number that's greater than 33.5 and less than 35.25. And t is an integer. There's only two possibilities for t. T is going to be 34 or t is going to be 35. So let's write those answers down. If I substitute 34 in for t into these formulas up here, I get x equals 3 and y equals 5. Now let's substitute in t equals 35. The other ordered pair that's going to be two positive solutions is 10 and 1. Now let's do an applied problem. We're selling short sleeve t-shirts and long sleeve t-shirts. Short sleeve t-shirts sell for $12. Long sleeve t-shirts sell for $20. We raise $84. How many of each are sold? I encourage you to pause the video and see if you can solve this yourself. Let's let X be the number of short sleeve t-shirts. X equals number of short sleeve t-shirts, and Y equals number of long sleeve t-shirts. So my equation here is going to be 12x plus 20y equals 84. The GCD of 12 and 20 is 4. 4 does divide 84, so we are going to get solutions. So we need to get a specific solution, and then we need to force the positives. So we might use the Euclidean algorithm or some other means. Let's see here. If I turn this into 24 and I turn that into 60, I think that would take care of it. 12 times 2 is 24, and 20 times 3 is 60. So that is going to work. So x naught is 2 and y naught is 3. Using our formulas, x is equal to x naught plus b over d. Calculate b over d. B is 20, D is 4, so that's 5t. And y is equal to y naught, which is 3, minus a over d, 12 over 4, which is 3t. So I have 2 plus 5t needs to be greater than 0. 3 minus 3t needs to be greater than 0. 5t is greater than negative 2. T is greater than negative 2/5. And over here, we have negative 3t is greater than negative 3. Dividing by negative 3, we get t is less than 1. So the only thing that's greater than negative 2/5 and less than 1 is 0. So there's only going to be one solution, and it was my specific solution, 2, 3. Now we need to answer the question. We sold 2 short-sleeved and 3 long-sleeved t-shirts. There may have been more than one solution, but in this case there wasn't because I couldn't use any other t-values. This has been a video on linear Diophantine equations. I encourage you to do more examples on your own. Have a great day.